This is like my third attempt at trying to go live. Every time I've tried, uh, something's gone wrong. Either the mic hasn't worked, and I've been on here for about an hour, um, or what else happened? And yeah, I was just going on here to try something new. I've been following this tutorial, build your own Lisp with C. Yeah, going through each chapter. I'm up to chapter 7. Um, and it's been interesting so far. If you would like to follow along or do this tutorial yourself, I left the link in the description down below. Um, yeah, yeah. So a little bit about my background with C. I've probably used C maybe 2 or 3 times. I'm not a computer science student. I've probably only taken maybe like 2 computer science or coding related classes. My background, or what I studied in college, was more mechanical and electronics. So I had a decent idea of some of these lower level languages, but haven't really used it in a production setting or build anything, I would say, meaningful. Um, However, as I was going through the basics, I knew this already, but just to highlight that as I was going through the basics here, uh, C is just really reminds me of Arduino. And I think Arduino is just a variation of C. Arduino? Nope, that's not it. Arduino. Let's see. Um, yeah. So to be honest, it's not a lot. Like the language, there's not a lot to the language. Um, in comparison to something like, I don't know, JavaScript or TypeScript or even Python. There's a lot of ways of doing the same thing. Um, and part of it is because of all the tooling and all the libraries that come with these languages. But C seemed pretty small. I mean, you can go through it here. There was a website here. Let's see, the website that I came across. Where the hell is it? C language. This is not it. If I find it, we will. I'll put it up. But anyway, my point here though is that the language is not. It's low level, but there's not a lot to the language itself. You feel like you could go through the entire language by just like following a few tutorials and solving some problems, and you'll have all the tooling that is required for you to feel, I would say, comfortable in the language. Um, with that said, because it is a lower language, it is doing a lot, and you have to basically write everything out. And there's good and bad to that. The good is that everything's very explicit. You can follow each thing that the computer is doing. You'll probably start asking or questioning things on like, why do we need to do this, or what is the reason for this, etc. And that could slow you down, and that could make things a little challenging to get started with. But the upside is that you actually know what is happening line by line uh, on the you could say hardware level. So it is pretty interesting going through it. So I am really up to chapter 6, 7 ish. So far, we talked about what is C, why you should learn it, and the purpose of this tutorial is that you'll be using C to build your own programming language, and that language would be Lisp, or your version of Lisp. Um, yeah, yeah. Um, Chapter 2 talks about setting it up locally, but if you don't want to set up or download the compiler, uh, and you have access to REPL it, I would just go into REPL it, and this is what I use whenever I'm teaching coding to a beginner. But I would go into REPL it, I would create a REPL and just use the C template. But yeah, that's basically it. Basics is like we went over the basics of C. There's probably a lot more to it, but I feel like these are probably the most important components. And chapter 4, an interactive prompt. So in this chapter, we basically go through how to create a REPL, a read, evaluate, print REPL. What does the L stand for? Loop, yes. Uh, and basically, what you should be able to do, what you do in a REPL, like in Python, is it's possible for you to like write one line of Python code and execute it, right? So if I come over here, I was running this before, and I write some Python code, let's simple Python code, 4 plus 10, it executes that line. It's reading, it's evaluating, it is printing the response, and then doing it all over again, right? And so in this chapter, you're basically creating a version of a REPL for uh, your language. Let's see. What else? Learned about this edit line tool. It basically allows for your REPL for you to be able to say like a history of your previous inputs, and then you can move up. You can move up in your history and reuse your history and change like a line to change something in your history, and then input it again. Learned about linking. So in order for your code to compile, you need to link libraries. So in this case here, we're linking the edit line library with your prompt.c file in order for you to compile it down into the binary that would be executed. Um, Also touched on preprocessors. What else? What did I have here? Preprocessors. They're programs that run before the compiler. They usually start with a hashtag or octothorpe. Um, some examples of using a preprocessor is that you can do a specific thing before you compile, which like if you can check to see if you're trying to compile this on a Windows machine, and if you are, maybe you'll import specific library. Um, yeah. Started learning a little bit about CMake, which I thought was interesting because you can kind of do that with CMake. How do you categorize CMake? What is CMake? Oh, a build system, powerful software build system. So it feels to me, what based off my understanding, you can set some of the rules in the preprocessor, or you can use CMake in order to set those rules before building your code. So it's interesting. What else? Learn about Boost, but nothing really here about that. Cool. Languages I thought was an interesting chapter. So languages. So the goal now is like we have this REPL that we've created in chapter 4 it was, and now in the REPL we're getting user input, and we want to be able to take that user input and compile it down into something that can be that can be run or ran. Um, And so what we're doing now is we are trying to create the grammar and the structure of our language so we can take that structure and uh, do the following steps in order to get it to something that your computer can run, right? That's the reason why we have to start learning about parsers. And so we are using this library called MPC, which allows you to basically build a parser combinator. And the parser combinator allows you to set your adjectives, your nouns, and your phrases. And you can use that in order to let's see what is it specify the grammar and the rules that your language understand. um cool. So to be 100% honest, I didn't really fully grasp this idea in this chapter. It wasn't until we got to, I think, parsing, where it made a little bit more sense. So in parsing, they talk about the Polish notation, and basically, if you have an expression, a mathematical expression like this, you could rewrite it in this notation here, where the operand, which is basically what you're doing, two values. So that's the operator, and then you have these expressions here, which is just a number, a parentheses like this, or it could be more expressions. So as you can imagine, it could be a recursive tree of expressions that need to be evaluated. Um, and this is, according to this documentation here, this is it resembles a uh, something that's used with Lisp, which is what we're trying to build. So that's the Polish notation. Um, cool. Going down here, we see about regular expressions. I've used regular expressions in the last 8 or 10 years or so since I've been coding. Usually, whenever I need to write a regular expression, if I need to find something within some text, for example, I don't know, a person's name within a blob of text or email within a blob of text, I would just use some regular expression generator. Probably not the best way to do it, but it would get the job done. So anyway, it was interesting going through some of this and seeing a little bit of how regular expressions are um, implemented on a lower level. Um, and so, yeah. Anyway, if you go down over here, you'll see that for the uh, Polish notation parser. This is what the grammar would look like. A number would have this regular expression, so it could take anything from 0 to 9. An operator can be any of these operators. An expression includes either a number or parentheses, left parentheses, with an operator or maybe another expression, uh, plus another parentheses. Plus, yeah. Yeah. Um, yeah. And so we take this Polish notation grammar, or the parser, and now what we do is we take the user input for each line of the REPL, and we pass it to the parser. And if it's a valid expression, here, it prints it out. Uh, Else, it'll print out any errors that come up. So if we try to run this, so this was the Python one. Try to run this parsing. We'll see if we put an invalid expression like hello, tells you there's an error. But if you give it a valid expression, which the expression, it could be plus 5 times 2 space 2. We'll see that it actually is valid, and it prints out the output. Cool. So that's how far I've got in this. Let's see. Let's keep going now. Evaluation. So, for what I understand, we have this grammar that we use to create the parser. We pass in the the text or each line of, let's say, code to the parser, and the parser lets us know if it is correct or not. If it is, I don't know, a valid input. I guess like if I try to connect this with, like, I don't know, something like Python or some other language, this would be a syntax error if you, I don't know, let's say with Python, if you forgot a comma between two parameters in a function, this would be one of those reasons why um, it throws an error if it doesn't meet the grammar that it understands. Yeah. Okay. Anyway, keep going here. Keep going here. So we have now the trees. Let's I've been using ChatGPT to help with some of this. Let's create a new one. Uh let's see. ChatGPT has definitely been the best tutor for some of this stuff. Mm, okay. I'm using MPC. Is that the library? MPC? Library to create grammar. To create grammar, to define grammar for my new programming language. I'm going to give it what it looks like. When I pass in text to the parser, it tells me if it is valid or not. Okay, that makes sense. How is this related to the abstract syntax tree? Let's ask that. How is this related to the abstract syntax tree? Okay. Interesting. So it says here that the MPC library not only checks if the input conforms to the grammar, also builds a data structure called an abstract syntax tree behind the scenes. The grammar rules describe how the input should be structured. The MPC parser matches the input text against these rules. Okay, cool. When a rule matches a part of the input, the parser creates a node in the AST. Okay, cool. Cool. That makes sense. A number node might be represented as a numeric literal, like 42. Okay. And let's see. An operator node might represent a symbol like that. An expression node. Okay. Hierarchy. Building AST. MPC all maps. See when it parses valid input. You can traverse this AST to understand the input structure. Why the AST matters. The AST is crucial because oh shit. Okay, so the MPC library validates the inputs against the grammar using some regular expressions, Creating the foundational data structure of the AST. Okay. Let's read. The internal structure is what we saw printed out by the program in the previous chapter. It's called the app. Oh, the app. So that is the tree right there. It's called. As the leaves of this tree are numbers and operators, the actual data to be processed. Okay. If we peek inside the mpc.h, we can have a look at the definition of mpc AST. mpc AST. Oh, okay. So if we do a search for that mpc AST, maybe to go to the definition mpc h mpc microparser. I really read that as microplastics. Too much microplastic news out there right now. Okay, cool. This is the type, the struct. Okay. It references itself because it can have children. Thus the reason or the need for recursion. Each node, the tag, contents, state. What the hell is a state here? Struct. Oh wait, this is itself. Okay, and these are the children. The first field is tag. When we printed out the tree, this was the information that preceded the contents of the node. It was a string containing a list of all the rules used to express the particular item. For example, that regex operator. The operator, okay, I see that. The operator is plus. The expression number of regex is 5, so it's a number. And then it has another expression, char times 2 number and a number. Okay. String containing a list of all the rules used to parse it. For example, this tag field is going to be important as it lets us see what parse rules have been used to create the node. The second field is contents. This will contain the actual contents of the node, such as blah, blah, blah. You'll notice for branches, this is empty. But for leaves, we can use to find the operator or number to use, okay? The next field is states. This contains information about what state the parser was in when it found this node, such as the line and the column header. We won't make use of this in our program. Finally, we see two fields that are going to help us traverse this tree. These are children num and children. Chapters for now you can think of as a list of the child nodes of this tree. Okay. Know that we can access a child node by accessing the fields using array notation. This is done by writing the field name children and suffixing it with square brackets, like so. Okay. For example, to access the first child in the node, we can use children 0. Notice that C counts its array indices from 0, like every other language. Because the type is a pointer to a struct, there's slightly different syntax to access its fields. We need to use an arrow instead of a dot. There's no fundamental. Okay. Recursion. Don't you just love some recursion? There's an odd thing about this tree. Each of the children are those trees. Okay. Yeah, just like indestructible. Okay. Talks about the children here. Basically, expressions can have expressions, and those can have expressions. Recursion. In C, we may write something like this: number of nodes, calling number of nodes. Yes. To write the poetry, we're going to write a recursive function. Okay. Finally getting to the meat and potatoes here. Okay, r.output. Okay. To evaluate the parts, we're going to write a recursive function. But before we get started, let's try and see what observations we can make about the structure of the tree we get as input. Try printing out some expressions using your program from the previous chapter. What do you notice? One observation is that if a node is tagged with a number, it is always a number, has no children, and we can just convert the contents to an integer. This will act as a base case in our recursion. Okay. What is that saying? That's saying that if it's a number, if the node is a number, it probably won't have children. Yeah, that makes sense, right? If a node is a number, it probably won't have children. Probably there's only recursion if there are parentheses, right? Yes. So if it's a number, that's the base case. And the base case is how you kind of like stop one of your recursive calls and then go back up the traversal. If a node is tagged with express and is not a number, we need to look at its second child. The first child is always that first child, and see which operator it is. Then we need to apply this operator to the evaluation of the remaining children, excluding the final child, which is always that. Those titles. Okay, if it's an expression, got it. The first node will always be less parentheses. The last node will be right. And then somewhere in the middle there's more shit going on. Yeah, and that more shit could be either just adding numbers or more expressions. Okay, this is our recursive case. This also needs to be done for the root node. Yes, it needs to start at the root node. Yes, makes sense. When we evaluate our tree, just like when counting the nodes, you'll need to accumulate the result. To represent this result, we'll use the C type long, which means a long integer. To detect the tag of a node, or to get a number from a node, you will need to make use of the tag and contents field. These are string fields, so we're going to have to learn a couple of string functions first. A to I, ASCII to integer, converts a char star to an integer, yeah. string compare takes an input to, and if they're equal, it returns 0. Okay, got that. String takes it as input into char and returns a pointer to the location of the second in the first, or 0 if the second is not a subtractor. Okay, we can use try which. It looks like this. Okay. Let's write this down. Type this out, whatever. Long eval. Okay. MPC AST T star T. If string T tag. Whoa. It's a number. Okay. Return T contents. Okay, what is this doing? This is basically saying if the node is a number, if the node's a number, go back up for a second. It actually said number. It does actually say number. Interesting. Okay. If node is a number, take the contents, which is going to be the actual number, but a string, and use this function, which converts the string into an integer. Cool. Keep going. The operator is always second child. The operator is always second child. The fuck does that mean? Char OP equals T. Children 1. Contents. What is that doing? The operator is always the second child. So if we had something like so, no. If we had an example, let's take this one over here. The operator is always second child. What does that mean? Let's come over here for a second. What does it mean that the operator is always second child? Example here. Always second child. Huh. Okay. Let's see, come back here. The operator is always saying, I guess Parser and AST like this, blah, blah, blah. Operator is always the second child. Oh, first, second? Is that what it is? This becomes this. The operator. The operator is always this. If tagged. Okay, let's see you're going through a tree. If the tree is tagged as a number, return it directly. Okay, that makes sense. The operator is always the second child. Okay. Second child is always the operator. Okay. So I guess what it's saying that if this is not a number, then this has to be an operator. Okay. I think that's all it's saying. We store the third child in X. We store the third child in X. So let's see. We stored the third child in X. Okay. Okay. Int I is equal to 3. Wow. Iterate. Combining. Let's let me just copy this for a second. And come over here. Help me understand this. Help me understand the entire the logic when traversing each node in the AST. Let's see. A node, okay, here's step-by-step breakdown. Okay. What I mean, a node tagged with number directly represents an integer. Okay, fine. Such nodes have no children, so we can extract their values, stop recursion there. That's our base case. That makes sense. Cool. How it's implemented, we see if it's tagged with a number, checking those blah, 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 convert contents. For example, for an AST node like, the actual return is just 42. Good. Keep going. Node tag with expression represents a mathematical expression, right? Makes sense. If it's not a number, it has children nodes. The second child is always the operator. The remaining children from the third onward are sub-expressions or numbers. Us. Yes. Yes, yes, yes. Yes. Yes, that makes sense. Extract OP is equal to plus. Yes, so you got the operand. Evaluate 1, which is just going to be equal to 1 because it's going to see it is a eval. It's just going to see it's a number. Eval op. What the hell is eval op? Evaluate. Oh, okay. Eval op makes sense. Eval op is just doing the actual math. Long eval op long x string, which is just the operation, long y. Okay. If string comp op, if it's a string of a plus sign, that you know you want to, if it is a string of a plus sign, you want to actually do addition, return x plus y. Yes, that makes sense. That makes sense. And then we would want to do that for everything. Whoa, whoa, whoa. We'd want to do that for everything. We want to do minus, we want to do multiplication, we want to do division, and we actually want to do the mathematical operation. Okay. The eval op makes sense. Eval op makes sense. Okay. Let's go back here for a second. Long x equal to eval t children 2. Okay. Iterate the remaining children and combining them. Int I is equal to 3 while string t children I tag expression. Okay. X is equal to eval up. Okay. And that's actually going to take the values that we've got, which are numbers, and the operation's a string, which will be converted into actual mathematical operations here. T children I. Okay. I plus plus. Okay. And then we want to return X. Boy, oh boy. Instead of printing the tree, we now want to print the results of the evaluation. Therefore, we need to pass the tree into our eval function and print the results we're getting using printf, and which is used for long type. Okay, we also need to remember to delete the output tree after we have done evaluating. Okay. First off, before I actually try this out, I get this part. I kind of get this part. No, and I specifically get here. I understand it and how it's calling here. Which, by the way, because this is C, I believe we need to define this function here, so it's aware of it during compile. So I get that. What's the part I don't get? I don't get this part. I don't get that part that much. And the while loop, I'm a little hairy on, but at least I'm honest. Okay. And well, let's see how it works, and then I can always come back to it another time. It's part of the great thing about learning. Okay, so we want to use it now. So I'm going to take it. Long result is equal to eval, which is the function that we created. Printf. This is painful, but I will do it anyway. Copying. You need to have a little. Needs to be a little difficult. That's how you learn. So that's handling the long value, and that's the result. Okay. And then we need to delete it, like it said, npc AST delete. Okay. Put that there. Okay. So instead of it printing out the abstract syntax tree, what it's going to do instead is that it's going to take the abstract syntax tree, it's going to recurse it to create the nodes of this tree. Well, it's not going to create a tree. No, it's already a tree. What it's going to do is it's going to traverse the tree, and in that tree you have these nodes, and the nodes could be a number, an expression. What else can it be? Number, expression, or a regex. Yes. I believe. Yes. Why am I okay? Sure. But you have these nodes, and through those nodes, you're able to kind of like figure out which one's a number, and it knows which one's an operation, and it continues traversing through the tree recursively until it finally gets to numbers and operations. And then when at the base or the leaf nodes, when you have nodes and operations together, you're able to start evaluating them, and you start bubbling up. Bubbling up, is that the right word? You start recursing upwards the stack trace and solve the expressions. Yeah. Let's come back here. Let's see what happens. Let's build it. Right there. Okay. AST type. Come here, so we know it's probably like so. MPC AST. If I do a quick search like that, is that correct? Oh, it's all lowercase, so make that like so. Come back here. 3011, 11, 30, 11 right here. Here. Okay, come back so. Warning generated. Non-void function does not return a value in all control paths. Parsing 13.1. 13.1. Ooh, interesting. Okay. Did I do something? Oh, I need to put the return there in case none of these conditions are true. Okay. Try again. Built. Parsing. Let's put in something that's not valid. Nice. So that still works. Let's put something that's valid. So plus 10.1. What the fuck? Segmentation fault. Interesting. Let's try again. Let's try the one that they gave us here. Segmentation fault. Why is it failing? Why is it failing? Well, let me see something here. What's the best way to learn a language? No. To debug segmentation fault. Segmentation fault. C. The best approach to use a debugger like GDB. Compile your code with -G flag to include debug information. Run the program within GDB. Okay. Compile your C program with the -G flag. Is it just something simple as this? I mean, I don't know. Is it something simple as just putting -G? Okay. And then GDB? It's not even an option. Okay, let's see. So I've been using Nix to download all my packages. So let's see if Nix has a GDB. GDB. Okay, it is there. System packages. Okay. So I have a file where I manage everything on my computer with Nix. Okay. Apply. Yeah, I'm still really new to Nix, so there's errors like these that I would not not be able to solve, but you know. Oh, okay, so that doesn't work for Mac here, I see. Okay. Okay, so that probably is not, if I go back to the Nix page, GDB, yeah, it does say it's supported for a Mac. So why doesn't it work? I don't think I have the interest of time to debug this. So what I will do is I will copy this. I will come over here and say, this is giving me a segmentation fault. Fix it, please. I really need to set up my cursor so that way I could just ask GPT on the side, but I'll do that later. Avoid division by 0. Is that what I did before? Did not do that, did I? Oh, that shit's not there. Okay, never mind. Ooh, double deletion of R output. That's something that seems wrong. That definitely seems wrong. Okay, that just might be it, to be honest with you. Like, what does it mean when they're segmented? What does it mean when the error is segmentation fault? What does that mean? Do you know what it means? I mean, when a program tries to access a memory place not allowed to access, makes sense. Basically, I guess what ended up happening was that I was deleting it and I was trying to access it again. And that's the reason why it would fail. So no need to use GDB and all that. This is just freaking, I guess, common sense there. So let's try this again. Build, compiled, or build, yeah, sure, whatever. And We'll come back to this interesting stuff. And let's run it. Parsing. Okay, so let's give it a valid expression. Plus 10 and 1. Freaking works. Nice. Let's try another one here. Let's try one of these over here. That should be 97. And it does work. Cool. That's pretty cool. Alrighty, I've been on here now for about close to an hour. This doesn't include the 2 attempts that I failed at doing this. But yeah, I'm gonna keep going here. Before I go here, I just wanted to say I've been coding now for about 8 to 10 years, and I think it's interesting, like using higher level languages because you can build things really fast. And I've had some foundation, some computer science foundation, and I've always had to take it out whenever I have to solve specific things. And it's nice going through some of this because it kind of refreshes my mind with a lot of this stuff that I've learned before or maybe had holes in my understanding. So yeah, I think this is pretty cool. And thank you to the engineer who suggested to me. And there's Raban. He suggested to me to he said that every software engineer should learn how a compiler and an interpreter works. And so and he suggested this tutorial. So I think this is already starting to be a great learning opportunity. And I hope for anyone watching this, it's interesting. I don't know if I'm going to do another live. We'll see how it goes. But yeah, let me know what you guys think. That's it.